Good afternoon. My name is Natasha Goyle.
I'm Madeline Hutton.
I'm Kevin Mao. I'm Walter Roper.
And I'm Sonia Sadafar. Together we worked on fabricating surface acoustic wave devices in a clean room and applying these devices.
So in this presentation, we're going to talk about the clean room and what it is, what we made in the clean room, surface acoustic wave devices, also known as SAW devices, the data we extracted from these devices, as well as an application with these devices as microbalances. But just by looking at the name, you might think that the clean room is clean as in sterile. This is not entirely true. A clean room is essentially a lab environment in which the atmospheric conditions are highly regulated. This means things like humidity, temperature, air pressure, and number of particles are highly regulated. So to give you guys an example of how clean this clean room really is, let's take a typical, somewhat urban environment like New Brunswick. So in a square meter, there's about 35 million particles in the air. In a clean room, in a square meter, there are about 10 to 350, depending on the particle size. This type of environment is very important to our project. This is because we're working on the micro scale. So to give you a little perspective, a piece of hair is about 75 microns thick. The smallest element on our device is about 8 microns thick. So you can imagine that if a hair were to fall on a device, during the fabrication process, this could damage the device and the integrity of the device as well. So in order to keep the clean room clean, you can see in the bottom right picture that we had to wear safety lab clothing. These included hairnets, safety goggles, gloves, and shoe coverings. This was not only to protect us from the chemicals we were using, but to protect the clean room from the potential dust we could let in. Clean rooms professionally are typically used in life sciences, biotechnology, and semiconductor manufacturing, which is what we did in the clean room, and essentially any other field where the products being made were sensitive to environmental pollutants.
So without the use of a clean room, the fabrication of surface acoustic wave devices, or SAW devices, would not nearly be as efficient. SAW devices function through the use of piezoelectricity, interdigital transducers, or IDTs, and surface acoustic waves. Piezoelectricity is caused by the stress and pressure of crystal. Not all material is piezoelectric. Only certain crystals like quartz are. Electrical impulses cause the crystal to contract and expand. And due to the contraction and expansion, mechanical energy in the form of waves is produced. IDTs are formed by a finger-like pattern made out of aluminum. Electrical energy is transferred into the first IDT. This causes the piezoelectric material underneath the IDT to convert the electrical energy into mechanical energy in the form of waves. The waves go across the device to the second IDT. At this point, the energy is converted back into electrical energy. So basically what our device does is it takes electrical energy, converts it to mechanical energy, and then back into electrical energy. The number of fingers in the IDT, the spacing between the fingers, and the spacing between the IDT all determine what kind of frequency are able to go across the circuit effectively.
Since only certain frequencies are allowed to go through the circuit effectively, SAW devices are often used as frequency filters. Frequency filters work through the principles of wave interference. If the waves resonating across the IDTs are in phase, they cause constructive interference. These waves and their associated frequencies are the waves that are allowed through the device. Meanwhile, if the waves across the IDTs are resonating and are out of phase, this causes destructive interference. These are the waves and their associated frequencies that are not allowed through the device because the resonating waves simply cancel each other out. Applications of the SAW filter are used in everyday appliances like radios and cell phones. Newer research is being done to using SAW devices as biosensors. By detecting small changes in frequency, they can be related to small changes in mass, and a SAW device can be used as a microbalance.
The first two steps in SAW device fabrication are sample cleaning and electron beam physical vapor deposition. Due to time constraints, these two steps were already done for us, so we just started off with 5 aluminum-coated clean samples. The first step we did was spin coating. In this step, we securely vacuumed the sample onto the spinner and slowly added drops of photoresist to the center of the sample until the whole surface was covered. To ensure the purity of this photoresist, we made sure the tip of the dropper did not touch the bottle or the sample itself. Also, to make sure the photoresist was clean, we dropped a few drops of photoresist onto the rim of the machine before the actual process. We spun the samples at 2 speeds, 500 RPM, and 4,000 RPM to spread out the photoresist evenly. After spin coating, we soft bake the samples to anneal any stresses introduced during spin coating to increase the adhesion of the photoresist to the sample and to further dry the samples. The next step is UV exposure. In this step, we used a method called contact printing, in which a pre-made mask with a pattern on it was brought into contact with our sample. UV light was then shined through the mask at the sample, chemically altering the photoresist. The samples were then put in a developer, which ate away the chemically altered photoresist so that only the pattern from the mask remained. This developing time varied, but they were generally all around 1 minute long. And we then rinsed out the sample in distilled water and dried it with high pressure nitrogen gas and another bake. The final step was aluminum etching. In this step, we put the sample first in potassium hydroxide, which oxidized the aluminum, and then in potassium ferrocyanide, which dissolved the oxide aluminum. The etching time varied greatly. For the samples in bigger petri dishes could be agitated more, so it etched faster. We left a layer of photoresist on top of the aluminum to prevent it from corroding. This method of using photoresist as a protective layer is called passivation.
Next up in the process was the biogen microbalance. For this procedure, we originally wanted to use our own fabricated microchips to measure the weight of the biogen and change the frequency. Unfortunately, we could not, for our filters had too small devices and too small electrodes. Instead, we used what was called a QCM, or a quartz crystal microbalance, shown right here. For this procedure, we put the QCM, well, the QCM was made better because it's a sensor and a bigger electrode and bigger device. We placed the QCM on a network analyzer machine, then added biotin. The biotin was in solution, we added 20 microliters per trial. We went from 20 microliters to 100 microliters, each time measuring the frequency and the amplitude changes from the biotin solution. And then we measured change in frequency to calculate the change in mass.
So after the samples were out of the clean room, it was time to take data like amplitude as well as frequency using the network analyzer pictured on the bottom right. As you can see in the top left picture, there are multiple devices on each sample. To test the devices, we used the cables coming out of the network analyzer on the bottom right and put them on a probe station where the device was. At each end of the cable, there were very small probes. These were then lowered on the electrode testing pads. To lowering the pads is very important in getting a clean signal because if the pads were pressed too hard by the probes, this could also damage the device and give a bad signal. If the probes were unevenly placed, maybe one off the testing pad, this could also lead to a bad signal. After the data was collected using the network analyzer, the data was sent to the computer for further analysis.
After collecting the data on our SAW device, we got this as a raw data. This graph shows the amplitude of the waves, which tells us the signal strength of the waves, along with the frequency of the waves. What this graph tells us is that the devices we created were functional filters. We know this from the 3 modes that appeared, mode 1, mode 2, and mode 3. The waves in these modes are the waves that experience constructive interference, and the waves that are going to be allowed through the device and have a stronger signal strength. The waves that are not in the modes are the waves that experience destructive interference and therefore have a much lower signal strength and will not be allowed through the device. We also analyzed the bandwidth and the operating frequency of these devices. The bandwidth is the range of frequencies that will be allowed through the device for each mode. For example, in sample for device 2, the bandwidth was 13 megahertz, meaning that from 441 megahertz to 454 megahertz, these were the frequencies that were allowed through the device. We also calculated the peak operating frequency, which is the frequency that is allowed through the device best, because it has the highest signal strength. We calculated this from analyzing the data points at the top of each mode, and that gave us our peak operating frequency, which there can be more than one for each mode. From this graph, it was hard to get anything more out of it because there was so much data on it, and there was also a lot of external and common noise present during data collection. So we decided to break down the data even further. This graph shows the peak operating frequencies of the 10 devices from 5 different samples and for 3 different modes. The linear horizontal trend tells us that the peak operating frequencies for the 10 different devices from 5 different samples were more or less around the same number. This, along with the low standard deviation, tells us that the microfabrication process was not only successful in creating functional filters, but also filters that provided consistent and reliable results.
This graph shows the data from the Microbalance procedure. As shown here, each addition of 20 microliters of biogen, both the frequency and the amplitude decrease. This is due to the same piezoelectric effect of the normal saw filters. As you add the mass to the biogen scale, the amplitude was decreased because of the added stiffness of the mass pressure on the biogen on the quartz crystal microbalance. The frequency was decreased because the added stiffness changed the interference of resonance structures inside the actual wave. This is shown more clearly in this graph. As shown here, there's an actual correlation between the change in frequency and the addition of volume of biogen. Using the equation down here, you can actually calculate the exact mass of the biogen we added. You also notice here, it's pretty much a straight line up to 60 micrometers. There are two causes for this error here. Firstly, due to pipetting, adding very small microliters of biogen can cause some errors, and also due to the carrier capacity of the QCM. The QCM device has a very small area for actual biogen placement. Because of this, any biogen placed outside this area will not be registered on the scale. Thus, as around here, it begins to curve off up to the carrying capacity, where no longer will the change to energy frequency addition.
Our goals were to create solid devices and analyze their applications as filters and microbalances. Through the microfabrication process, we learned the importance of the clean room. As you start building smaller devices, every dust particle in the air can affect the quality of the device. Therefore, the clean room was an essential part to microfabrication. Our SAW filters had positive results. Each of the 10 devices showed 3 modes with similar frequencies, as seen in the horizontal trend of the graph. Our microbalances also had positive results. They showed the correlation between frequency and mass. They showed that decrease in frequency is proportional to the increase in mass. There's still further tests that can be done with these devices. As mentioned, the biosensor has a carrying capacity. Once the surface area of the biosensor is full, it can no longer detect the change in frequency or the change in mass. We need to understand the minimum and maximum limitations of the biosensor to fully understand the applications of the device. We also need to understand the correlation between the experimental data and the theoretical data. The SAW filter should have shown a graph where mode 1 had the highest frequency. However, our mode 2 had the highest amplitude to the graph. Right now, diabetes is an important and growing disease in the country. Diabetic patients need to draw blood multiple times a day. Our microbalances only need microliters of blood to detect the sugar levels. Eventually, these biosensors will be incorporated in a device that can automatically regulate the sugar levels in a diabetic patient. Solar cells are another use for our SAW filters. As of right now, solar cells are not very efficient. They produce a lot of heat energy as a waste product. Our SAW filters can take that heat energy and convert it back into usable energy. We would like to take this time to thank our mentors in the Microelectronics Research Laboratory and the Rutgers Department of Electrical and Computer Engineering, Dr. Pavel Reyes and Dr. Warren Lai.
We'd also like to thank the cleanroom technician, Robert Lorber. There was a time when the cleanroom wasn't working, and he worked very hard for us to get back in there and finish this project.
We'd also like to thank the New Jersey Government School of Engineering and Technology Director, Eileen Rosen, for making all of this possible.
System Director John Patrick Antoine, who's helped during update and paper writing.
Of course, our RTA, Jeff Kowalski, for all support in taking us to where we need to be. And also the Rutgers School of Engineering, Dean Thomas Harris, and our sponsors for giving us this opportunity. Any questions for us?
Can you explain a little bit how the presence of biotin can change the frequency of the electricity going through the device?
Sure. So the frequency gets changed because as you add biotin to the QCM, the actual material, the quartz, it decreases, it gets denser, and the mass makes it smaller in thickness. And the interference patterns I talked about earlier with constructive and destructive interference, and whether or not the waves are in phase, depends on the distance from one end to the other end. So if the biotin shortens this distance, it changes the interference patterns, and that changes what frequencies will be allowed through the device.
Does it matter what molecule you add in the solution? Is it just the mass?
Just the mass.
So,
No, just the mathematics. The material does not.
Biotin was a good representative of.
so if I add the molecule with the same molecular weight, you would detect the same
Yes.
thing. So how can you use it as a biosensor to detect biotech?
It's more as a microbalance rather than a biosensor. I mean, it's a biosensor that detects mass.
Okay.
So, any other questions?
Would you elaborate why there were 3 modes? I believe the UIDT have only one spacing.
So the reason that happens is because there's the pattern that the wave interference follows. There is a fundamental frequency, and then there are several harmonics that follow. The fundamental frequency is the lowest frequency where the waves are in phase, which means that the loads match exactly and they cause constructive interference. But they can be also in phase in higher frequencies, and those are the first and second and third harmonics. So a fundamental frequency is the first mode, and our harmonics are the second and third modes. In a device that could in a device for a filter, you could actually tune from one mode to the other, which is how you can change the frequency that you pick up.
So that's why, in theory, the fundamental mode should have been the highest intensity.
Yes.
Thank you.
So how long does it take to fabricate the device from start to finish?
It took us a couple days. In the lab, it took us actually a couple days, but in theory, it could be completed in about maybe 2 days if we worked closely the entire day. The first 2 stages actually take a long time, about 7 hours for the electron beam deposition.
And you make several at a time?
Yes.
Each chip contains many, like it's the device is the actual, you can only see it on the microscope. Any other questions?
Thank you.